Let's take a look at example 2.1.1 from our text, solution for a linear equation. So what they ask us to do in this problem here is to use the method of separation of variables to obtain a solution to the equation 2.1.11 given in our book. So if we go down here, this equation in our book, on page 45 of our textbook, we have this expression here, dx dt plus ax is equal to b. So general linear first order form. You're going to see throughout our study, we'll see many models that are going to follow the same form here. So they want us to take this form here and go ahead and obtain a solution using separation of variables. So now that we've had the opportunity to read through the problem statement, take a look at what they give us and what they're asking us to solve for, we now want to create our setup page. On our setup page, we want to write down clearly all the information they give us in the problem statement in any given diagrams and what they're asking us to solve for. And keep these labeled and separate there so we can reference back to this first page as we're going through our solution. So what do they give us? Well, they give us equation 2.1.11 on page 45 of our text, dx dt plus ax is equal to b. What do they ask us to solve for? Well, they want us to find the solution using the method of separation of variables. So down below on the same setup page, we like to write down any assumptions we're going to make, maybe a plan of attack for the problem, anything they give us in the problem statement that's known. So in this one here, they have this given equation here, and what we do know about this, beyond what we've written above in our given and find section, is that a is a constant from our a right here, b is a constant here, and a is not equal to 0. Our plan of attack, we're going to use separation of variables. So now that we have our setup page complete, clearly see everything they've given us, what they're asking us to solve for, any assumptions we're making, and reference back to that as needed. Now we want to go ahead with our solution. So next we need to integrate both sides of the equation separately. So in order to integrate them both separately, we need to move the equation around. We do that by multiplying both sides by dt. It takes our dt from the denominator over here, brings it over to the right side. On the right side, we divide by b minus ax to bring that over on the bottom of the denominator over here. So we have dx over b minus ax is equal to dt. So now that we have that there, we want to reduce and simplify just a little bit. We'll pull that dx out here. Leave this as 1 over b minus ax. This is equal to now our dt. So there, we have a great form that we can now easily take the integral of both sides. So we do that there, integral, the limits of integration from x of 0 to x of t over time of, 1 over b minus ax dx is equal to our integral from 0 to t dt. So the right-hand side of the equation here, this right integral right here is pretty straightforward. The integral of dt simply becomes t down here. So now we're just left with dealing with the integral on the left-hand side of our equation, integral from x of 0 to x of t of 1 over b minus ax dx. So how do we solve this? Well, we can take a look at our tables of integrals, look at the general form of this. What we're going to do here for this specific case is we're going to use u substitution to integrate the left-hand side of this equation here. So let's look at just this left-hand side. We've already dealt with the right-hand side here. We got the integral with our limits of integration here of our 1 over b minus ax dx, where a is not equal to 0. So from this here, we're now going to begin our u substitution. So as we recall from calculus, we're doing u substitution. We need to make a decision now when we look at the general form here of what we want to be u and what's going to be our du. And how is that going to work as we move forward? Sometimes we can play it out. We've done enough of these. We know what we want to do. Other times we may try something that doesn't quite work. We may need to go back and choose a different u. In this case here, in a general rule of thumb, let's take a look and try to have the denominator be equal to u. So the denominator of our equation here is b minus ax. We'll say that u is equal to b minus ax. So our du is the derivative of that. The derivative of b minus ax is simply negative a dx. So now I have a u and my du. So from this here, my du, we have a dx in there. We want to solve for this dx. So we rearrange, solve for this. We end up with dx is equal to negative 1 over a du. Make sure we pay attention to our sign convention throughout this problem. We don't want to drop anything. So with this expression now for dx in terms of our du, we can now make that substitution. So we look up top there and we say, okay, what do I have going on? I know my u, I know a dx now, so I can replace this here, my denominator, by our u that we chose right there. U is b minus ax. We chose that to be that, so that goes there as our u. Now our dx we've solved for here from our du expression by taking the derivative of our u. So we end up with this over here. Dx is now negative 1 over a du. So with this here, we now have the expression that we can see below. Move this down just a little bit here. We can see now we have the integral from x of 0 to x of t of, now once we do our substitution, 1 over u times negative 1 over a du. So as you can guess, the next step from here, we're going to rearrange this just a little bit on the next page. So here's where we ended up now. We have the integral of 1 over u times our negative 1 over a du. We can take that 1 over a, pull it out front here. So we have negative 1 over a times 1 over u du here. And the reason we do that there is we know our a is a constant. We saw that in our setup page here under our assumptions there from the problem. So a is a constant. What does that mean? Well, we can pull a constant out front of the integral. So we can pull this negative 1 over a out front of the integral before we do our integration here. So now we have 1 over a negative times the integral from x of 0 to x of t of 1 over u du. Now that's a pretty straightforward integral right there that we can look up from any basic table of integrals. Move this up just a little bit there. So if we look that up, we see our general form here. We can do, okay, the integral of 1 over u du is the natural log of the magnitude of u plus a constant c. So we have our negative 1 over a out front, then we have our general form here, the natural log of u plus c, with our limits over here going from x of 0 to x of t. So now we can rearrange and replace the u's with their actual values from above. So we had our u, we'd already said before on our previous page that u we let equal to b minus ax, so we can swap that back in now. So this is equal to negative 1 over a times the natural log of our value here for u, b minus ax, plus c, evaluated from x of 0 to x of t. So now the next step in our solution is to plug in those limits. We can plug those limits into the equation here. Now we have two of these outline functions. We can pull our negative 1 over a out front of this entire expression here. Plug in our upper limit onto this side here. Natural log of b minus a x of t minus the natural log of b minus a x of 0, all equal to t. So we want to reduce and simplify a little bit more. So next we want to multiply both sides by a negative a to get rid of this on this side and add it over to this side here. We do that there. What we end up with is the natural log of b minus ax of t minus the natural log of b minus ax of 0 equal to now my negative at, which is a little bit cleaner looking equation than we had above there. We got rid of that, move it over to this side here. Then the next thing we're going to do is actually deal with these natural logs. We can take the natural logs from this here. What we end up with after we do that is we get b minus ax of t is equal to e to the exponent negative at times b minus ax of 0 right there. So there is our solution after we've taken the natural logs. So from there, we want to ask ourselves, okay, what are we looking for? We're looking for the solution to that equation 2.1.11 from our textbook using separation of variables. To get that solution, we really want to solve for it in terms of x of t here. So we can rearrange, solve for our x of t, so we can get rid of this right here, divide through by everything to get our x of t by itself, move the b over the other side, divide through by the a, we move the b over there, we got our negative b there, divide by our a here, negative a, left with just our x of t. So divide by negative a, divide by negative a, have that negative b there, then we move over there, we're only left with our x of t. So from this right here, move this up a little bit for you here, x of e to the negative at times b minus ax of 0 all over my negative a down here, moving it over from that there, plus b over a, because this would have been a minus, minus b over a there, double negative, cancels to a positive there. Then we end up with, when we rearrange this, simplify this down a little bit, divide everything through by our a, x of t is equal to b over a, move that to this side, of x naught minus b b over a times e to the negative at. And this is the general form that we see in equation 2.1.12 in our textbooks. That's a good double check. We can reference back to that. So let's first start by taking a look at this problem in MATLAB here. And let's try to plot it using MATLAB code. So we have a script file open over here, and there's two different ways that we can solve this problem. One, we could plug in all those values that we saw, x naught, a and b, which is exactly what I've done here. I've plugged that in, so I've just used that expression that we just wrote out there with the variables and the constants plugged in with their values there. So we have y is equal to 3 times the exponent to the negative 2t plus 10 times 1 minus the exponent to the negative 2t over here. So I can go ahead and graph that. I'm going to go from 0 to 2 using steps of 0.2 along the way. Label my two axes and put a title on that there. So that's the first thing I'm going to do. I'm going to come up top, hit run. I do that, end up with this graph right here. So we can see, okay, there it is from 0 to 2. Have my axes labeled as t and x of t over here, and my title right there. Now, the other way I can run this, I can close out of this here, comment out everything here, come down and do this in terms of variables. So I uncomment this here, and now I leave this now as a general expression here rather than plugging in the variables. So I can comment this guy out here and just use this down here. So I have my y given by in terms of these values here, where I now define them as x of 0 equals 3, a equals 2, and b equals 20, and those will plug right in now for this here. I can hit the run button, end up with the same graph here, regardless of how I did this. But the benefit of using this code here now is the fact that I can easily change this. So these values I can quickly change right here within my script file, and it'll change everything in my graph. I don't have to go through, resolve it, write out another equation. I can quickly change them right there. So now I'm going to go through the solution plotting using Excel rather than MATLAB. Sometimes Excel is a little bit quicker and easy to use for these simple problems right here if we need to see a plot rather than writing out a whole MATLAB script. So within this problem here, what I've done, if I click on this cell up top here, you can see there is that general equation that we ended with our hand solution for this problem there, where we've plugged in our values now based upon x naught is equal to 3, a is equal to 2, and b is equal to 20 there. So I've plugged those in already. We could have used those as variables just as we did in MATLAB and put them in individual cells and quickly changed them. For the simplicity of this problem here, I plug them in for these known values here. And then what I've done is I've left my t's in here, and my t's I have from 0 to 2 again as 0.2 intervals in between them, and I've just labeled those right over here. So I now have entire column for my t values, and I now have an expression here. As I step down through each of these, you can see the equation changing as those t values are plugged into this general equation here. From that, I can graph both of these just as a simple line plot here, and this is what I end up with for my solution. And to graph that, if you didn't know, you can highlight those, insert, come down over here, select this graph right there, just like that.